Of course, we also have to recognise that this is it's a personal journey. Depending on if you decide to or are applying STAMP or STPA in whatever it is you're doing, it is a bit of a journey. And for those with sharp eyes, yes, that is Mount Everest. And I'm using that for various metaphorical reasons, but just recognising this is the beginning of you developing your necessary knowledge and mindset about how to use STAMP and STPA. And of course, I want to be able to support your skills development and help you get fantastic results, recognising it is a personal journey for you yourself, but also for your project, your organisation. And depending on the nature of the project you're working on and the nature of the culture of the project or organisation you work with, that can present its own challenges if you can read between the lines. So yeah, that's sort of where we are with that. Now, with that said, what you'll see today is part of what's included in my upcoming STAMP Foundation training program or coaching program. And so this is giving you a little bit about the what, the why, and the basic how related to STPA and CAST. And if you're familiar with the Bloom's taxonomy, we'll be talking mainly about developing your knowledge and comprehension and showing you a little bit of the application. But of course, everything else, we haven't got the time to go through everything else today, and it does take some time, especially to develop the thinking and practical skills. Now, of course, in terms of my program, I have a foundation training course, and the intention of that is to set you up with the basics, with the intention that, of course, you're going to need help and support on that journey. And so I have got group programs, both private and public. And of course, if you wanted help in your organisation, I can arrange to support a private project or support a private group, either doing the work with you or independently reviewing that work and giving you some confidence that you're not too far off the track. Now, the objectives of today are to appreciate the basic process of STPA and CAST. I've already appreciate how to apply it. Actually, hands up. Let's just do a quick survey. Hands up. Who has? Let's have a look. Who has watched the live stream videos? Any of the live stream videos that I did on LinkedIn over the last few weeks? If you want to raise your hand for me using the button at the bottom, that would be appreciated. So we've got a few there so far. Let's just have a look. Why is it not counting? No, it's not that one. Okay, so we've got a few there. That's good. And just type in the chat, were they sort of helpful or hindering? Did it sort of leave some open questions? Or what was your general view of that run through of the accident report? There we go. We've got a few. Sorry, no time. That's fine, Jose. I did. Fantastic. Okay. Any others? If not, it's okay. It just means that today I'll go through that a bit more in detail than I would have done. Thank you, Karel. Than I would have done normally, would have done today. Okay, so we hopefully recognise the significant opportunity that STAMP, STPA and CAST present. And then, of course, I want to answer stupid, awkward, difficult questions. So please don't hesitate. If you have a question, there's a strong chance somebody else will have a similar question. And if you ask that question, not only will it benefit you, it'll benefit others. And of course, watch out for the questions that other people ask, because they may be a few steps ahead of you, and they may ask questions that you've not thought to ask yet. So there we go. We've got James. James says it's a useful way to explore the report, which I've also read. Fantastic. Thanks, James. And of course, at the end, I'd like to make an offer. Now, the offer is pretty basic. If you want to stick around and hear the offer, stick around at the end and we can talk about that. Great. So an outline then today. So we'll give a brief introduction outline, which I've just done. I'm going to prime your mind with some core concepts, and I'll be interested to know if you recognise those core concepts yourselves, whether you've already come across them. We'll give you a brief overview of STPA. We'll give you a brief overview of CAST. We'll give the case study an introduction. We'll talk about and look at the control structure models. Now, if you've seen the videos, I scribbled them down on the Miro Infinite whiteboard. And then this afternoon, I've turned them into something a bit more formalised, so it's a bit cleaner, a bit easier. James, are you raising your hand to ask a question? No, okay, that's fine. No worries. There we go. And then we'll talk through the case study and talk about any questions or comments you've got about STPA or CAST. And then we'll talk about some conclusions and observations. We'll share some reflections, some questions, and then, of course, the offer, how to get help and support. Okay, so who am I? You probably already know who I am from all of the things I post on LinkedIn, but I'll just give you a quick rundown as a quick reminder and to catch up with some of the things I've been up to over the last couple of years. So I've got 2 degrees, a Bachelor of Engineering Honours in Aerospace Engineering and a self-funded Master of Science degree in Safety Critical Systems Engineering from the University of York in the UK. I've also visited MIT on a number of occasions over the last sort of 11 years since 2014. I've been most years to the stamp workshop, and I've also taken part in Dr. John Thomas's STPA Hazard Analysis course November last year, which was an interesting experience. I've also been fortunate enough to attend the University of Southern California's aircraft accident investigation course. I've got over 20 years now, I show my age, experience in system safety engineering and safety critical complex systems, mainly in the design, development and change of those, but also in operations and accident investigation. Now, just to quickly rattle through this, there's a whole list of all the different areas I've worked. I've highlighted the ones in green to emphasise those that are most recent. So mainly aerospace and defence, so defence systems safety, air traffic control, weapons systems, such as surface-to-air missile systems, torpedoes, things like that, military test ranges and facilities, nuclear weapons, oil and gas, automotive, rail, most recently healthcare, patient safety and healthcare IT, mining, robotics, autonomous systems, AI, various others, and then most recently in a lot of detail, nuclear submarines, submarine combat systems, and then, as I mentioned, space in terms of planetary protection. So my sort of experience is quite broad, and having that broad experience has enabled me to experience how safety and system safety and risk management is done across all of those domains, many of them regulated or highly regulated, but also the different language that those industries, those different domains use and how they deal with safety, risk and the concepts associated with it. Like in healthcare, they don't necessarily have a concept of risk or hazard in the conventional sense that you might do in aerospace and design of weapons, for example. So it's given me a bit of a unique perspective and an ability to talk across many domains, and problems that exist in one domain, there are solutions in other domains that can be read across or adapted. So that sort of gives me quite a broad experience. I'm also a guest lecturer at the Cranfield University in the UK on their accident analysis techniques course, where I talk about CAST. And I provide stamp STPA CAST consultancy, independent review, facilitation, training and coaching, both individuals, but also organisations and groups on a project. And I myself, as with everybody, I'm on a personal journey to learn, grow and serve others. Now, these are just some of the organisations I've worked with over the past 20 years, and those that I've highlighted with a red dotted line are just to emphasise those that are related in some way, the experience is related in some way to this case study, but also the most recent ones. So with the European Space Agency at the top, and then the Healthcare Services Safety Investigation Branch, Cranfield University, GE Aviation, BAE Systems, Kinetic and the Royal International Air Tattoo, which is an air show which has very often had the F35 flying around, as you saw from the photo on the landing page. That was 2024, that was. So quite a lot of sort of experience across the patch. Now, in terms of my journey with STAMP and STPA, it sort of began in the aftermath of this high-profile accident in the UK. So if you're not familiar with this is the Royal Air Force Nimrod aircraft accident that occurred in 2006. And in the aftermath of that, there was a Royal Air Force military board of inquiry that did an investigation. And then in the aftermath of that, given the scale of the loss of life, this was the single largest loss of life since the Falklands War in 1982. So it was a big deal. There was a separate inquiry called the Nimrod Review, which was run by a chap called Sir Charles Haddon Cave QC at the time. And whilst all his investigation was going on, and he was interviewing people and getting witness evidence, and going around and talking to various people, collecting evidence, I was an independent contractor working for a company called Kinetic in 2009, and I was tasked with leading a team of subject matter experts to perform an independent technical evaluation of this aircraft and its sister aircraft, the R1. And essentially review the designer safety case by the aircraft manufacturer BAE Systems at the time, and also what's called the operator safety case, which obviously was the RAF. And so myself and my team of subject matter experts spent a lot of time talking to people, visiting various places, crawling all over the aircraft, banging my head, cutting my head open on the bottom of the aircraft a few times. I was very close to the sort of front line of this, but not directly involved. And in fact, the person that I essentially replaced in that organisation to do this review, he was one of the people that were mentioned on the front page of the newspapers and in this report. So I was, I know a lot of the people mentioned in the report, including the witnesses. And this really shaped how I continued my career from that point forward. Now, this report was released in 2009, October, about now, 16 years ago. It's crazy. Essentially, I also started my self-funded masters at York, so going down the academic path, reading lots of books, reading very widely papers, doing a literature review, and learning more from an academic perspective. And this is when Professor Nancy Leveson from MIT, she sent out a draft copy in PDF of her second book, Engineering a Safer World. And that's when she introduced what Stamp, Cast and STPA was all about. And I remember quite vividly seeing the page with the control structure model on it, and seeing that now it included not only the, in my case, the Nimrod aircraft and the maintainers and the operators, the designer and the operational leadership, but it helped me to see how the issues I was witnessing firsthand and that are discussed in this report actually appear all over the control structure model. So, in this accident, yes, it was a fire and explosion, and fire and explosions are quite sort of basic and mechanical, if you like. But the reasons that aircraft got into the state that it was, and why those people unfortunately lost their lives, was because of issues with the control structure. And when I was learning to use fault tree analysis and failure modes and effects analysis and event trees and HAZOPs and all of these other weird and wonderful safety analysis methods, none of them allowed you to highlight these issues with the organisation. And so for me, it was sort of the start of the journey of learning what Stamp is all about. And then in 2014, I plucked up the courage and the finances to fly out there and see what it was all about and get stuck in. And since that point, I've been on a bit of a personal mission to sort of bring this to the masses, because I can see it. Not only would it have benefited me as a system safety engineer doing safety analysis, it would have also benefited me as an independent investigator looking at the organisational factors in an accident. So that's sort of my background, if you like. So my perspective as a system safety engineer, also having airworthiness certification engineer experience and as a safety investigator, having design and development operations and investigations experience, cross-industry domains, safety critical, regulated, fatal accidents, design thinking, systems thinking, a growth mindset, thinking that, we're what we're born with between our ears is something we can develop over time, so we can get smarter and better as we learn new things and try new things. I like to think of myself as a bit of a student explorer, a perpetual learner. So I'm always trying to learn new things and see, recognize I don't know what I don't know, and I have to, overcome those blind spots. I want to be an observer, a reporter. So the things that I'm doing, I want to observe and report to others so that they can follow on that path. I'm also a bit of a pioneer in some of the things I'm doing. I'm not sort of comfortable being called a pioneer or an expert, but I recognise that's how some people perceive the things that I'm doing. I'm a trainer and a coach, a marketer. And I include marketer because it's important to recognise that whenever anybody wants to try anything new, there is always going to be people, understandably, that don't want to try something new. They've already got what they've got. It seems to work, so let's just keep doing that until we have some really big reasons why we shouldn't. And of course, it's important to understand that when we're trying anything new, we have to go through that period of transformation. We have to go through the period of engaging other people and helping them learn about it so that they can have all their questions answered, have their objections addressed, and then help them on their way to getting results. Now, I always want to emphasize I'm not a religious fanatic or a zealot. I want to try and see what works. But if I see that it works and I'm getting good results with it, and the people I work with are getting good results, I want to help and promote that and move that forwards. But my focus is on getting results because people's lives, livelihoods, and legacies are at stake. So my personal aim is to grow and nurture a global cross-industry community and support them in getting fantastic results, going from talking to taking action and getting results. And that's what today is really all about. So I'm just going to prime your mind with some core concepts. But before I do that, I'm just going to check to make sure everybody's in. Yes, we've got everybody in. Ian says, sorry I'm late. It's okay, Ian. We're here. Thomas says, I'm concerned about the psychology issues within the pilot community. Think German wings. Fantastic. We can talk about that certainly later on. Thanks, Thomas. Okay, so let's keep going. So what I'd like you to do is if you can stick in the chat, type in the chat whether this is familiar with you. Yes, no, maybe, kind of. I could teach a class on it. Type in the chat. Teach class, fantastic. Got a few in there. Okay, that's good. Right, so this is a very, very basic control loop. And this, for me, this is like one of the two main core sort of concepts of what STAMP, STPA and CAST are all about. And if you can master this concept, it will move things on tremendously. So what we've got at the top here is we have what's called a controller. And that controller can represent a human, it can represent an organization, a group of humans, it can represent a technical controller, a software controller. And of course, that controller has some form of decision making within it. And that decision making essentially helps the controller decide what control actions and when those control actions should be provided. And those control actions are provided to a concept called a controlled process. Now, if you imagine you driving your car, you are the controller. The control process in this case is the movement of your vehicle from A to B. And of course, you're directly in control of your car and you provide control actions and you receive feedback from the car and your environment, which helps you make decisions about how fast to drive, how slow to drive, whether you should press the brakes or whether you should turn your headlights on or off. And of course, you also have some beliefs about that control process and about yourself and your capabilities. And those beliefs more sort of formally would be referred to as a process model or mental models if we're talking about a human controller. Excuse me. Pardon me. Now, of course, those beliefs, those mental models, process models, they're updated with feedback from the control process. And some of that feedback can be direct perception. So if we're talking about a human being, they can directly perceive things. But also you might receive feedback from somewhere else. There might be some sensors on the process that you're controlling, such as your pressure gauge, pressure warning. So if you've got low pressure in your tyres, your car, if it's got one fitted, might come up with an alert to say, hey, you've got some low pressure, you might want to change the way that you drive. And this is, for me, this is the most important core concept of STAMP. And I like to talk about this in the context of being a jigsaw piece. And so whenever we're doing any kind of STAMP-based analysis, whether it's STPA or CAST, we're looking to identify these jigsaw pieces and then see how they fit together in an overall control structure model, an overall jigsaw. So this is why I like to use the second metaphor of a jigsaw puzzle. So when we're trying to build a control structure model, they're essentially made of all little jigsaw pieces, little control loops, little control structures, control loops, and how they fit together overall in an overall structure. And you'll see in a moment some examples of that when we get into the case study. So on a scale of 0 to 10, what I'd like you to do is type in the chat On a scale of 0 to 10, how familiar are you with systems engineering as a concept or discipline? If you don't know anything, it's 0. If you know everything and could teach a course on it, if you could type 10 in the chat, that'd be great. And over time, that number will stabilise. Bear with me. So we've got some good numbers in there. We've got a few lower numbers where we haven't got any zeros so far or ones, so that's good. So that's fine, Mark. I can deal with that. That's good. Jose says 10, but he's always learning. Great, Jose. Fantastic. Okay, so in terms of systems safety engineering as a discipline, on a scale of 0 to 10, if you want to just give me an indication of where you are, 0 is you don't know anything, 10 is you could teach a degree on it. Got some 10s, got some 6s, some 10s, some, yep, okay, that's good. Okay, so that's a bit more variable, that's okay, it's not an issue. Okay. Great. Okay. Thank you. Fantastic. Okay. So in terms of we'll do this in 3 chunks then. So in terms of system theoretic accident model and processes as a foundational set of beliefs and theories and understanding, on a scale of 0 to 10, how familiar are you with STAMP itself? So that's the accident model, the underlying ideas, and then the processes itself. So it's a bit lower. Aidan's got a 0, that's fine. David's got a 1, Mike's got a 2, okay. David's got a 3. No, that's fine, that's a bit lower. We're not going to go into the detail of that today because we haven't got enough time. I will cover that in the foundation program to a certain level, but I would recommend having a look at the materials on the MIT STAMP website, because they've got a lot of videos on there that talk about these sort of foundational stuff. We're not going to go into that in detail today. Okay, so in terms of STP, oh, hang on. I'll give it a moment to reset. There we go. In terms of STPA then, 0 to 10, 0, you don't know anything, 10, you could do one in your sleep. Let me know. There we go. Okay, so we've got some good spread there. That's fine. Okay. Okay, good. Fantastic. And then the next one is cast. I'll just give it a second to reset. There we go. So 0 to 10, how familiar are you with cast? Got some numbers there. 1, 2, 2, 4, 3. Okay. Fantastic. Great. Well, we'll give you some of the basics today. I won't, in terms of the foundation course, I do have a foundation training which gives you the basics that lasts a day. And then, of course, once you're equipped with that, you can have a go. But you will need some support going beyond that, because it's not just a quick course and crack on. There is a lot of mindset aspects, a lot of thinking skills that you'll need to recognise and develop, and then, of course, practical skills tailored to whichever project you're working on and whether it's an accident or a new design that you're working on. So fantastic. Okay, so on a scale of 0 to 10 then, how familiar are you with this accident? Have you read the report? Have you watched the 5 hours, 5 hours of live streams the other week going through the report? So Ruben's got 0. Thanks, Ruben. Martin's got 1. That's fine. No worries. James has got 8. Great. James can lead the session, I think. Thomas has got 4. Raji's got 0. That's fine. That's not an issue. We could talk about it. So it's about this aircraft. If you're not familiar with this aircraft, this is a Lockheed Martin F35. I was just about to say Joint Strike Fighter, but that's not the right name anymore. Lightning II, I think it is. And having seen it at the air show, it is very loud. It is absolutely mind-blowingly loud. Single engine aircraft, very cool looking, very stealthy. And the F-35B variant, the VTOL, vertical takeoff and landing variant, is a sight to behold. But this is the A variant. This is a conventional takeoff and landing aircraft. Now, these pictures are borrowed from the website of the news article when I was first aware that this report came to being. And these pictures are representative of Eielson Air Force Base. So in January, it's clearly very, very cold. Excuse me. It's clearly very, very cold and wintry. And on the right-hand side is a picture from inside the air-conditioned, climate-conditioned hangar. So it's kept in a nice warm environment so people can work on it and not be exposed to the harsh environment. Right, there we go. So the foundations then. So what is STAMP in inverted commas? When somebody says STAMP, what are we actually talking about? Well, we're talking about the system theoretic accident causality model and some processes based upon that model. And it originates from Professor Nancy Leveson at MIT. She wrote about it at length in her second book, Engineering a Safer World. And there is actually a PDF copy of that book available for free from the MIT Press website. And I was very fortunate in 2016 to run a webinar with Professor Leveson, which we recorded and put onto my YouTube channel. If you've not already watched that and you want to hear about the principles and the basics from the proverbial horse's mouth, I recommend watching that YouTube video. I can put the links in the chat later on if you are interested. Otherwise, just search my name and STAMP on YouTube and you'll find it. So STAMP is an acronym that refers to an underlying accident causality model and some principles. So whenever somebody says STAMP, that is what we're really referring to is the causality model. We're not talking about the tools based on that model called STPA and CAST. We're just referring to the new causality model. So when somebody says, I'm going to do a STAMP analysis, there's some context that's unsaid. Are you using STAMP during design development or change of a system? Or are you using it to investigate an incident or an accident? And in which case you're using STPA or CAST. Now, what STAMP does, what the fundamental accident causality model does, is it broadens our safety focus beyond failures. And it allows us to expand that to include failures, but also what I call dangerous successes. So this is where the system has behaved as designed, and unfortunately, that has resulted in an accident. And this particular case study is a good example of a dangerous success. The aircraft believed that it was on the ground when it was still in flight, and so it behaved like it was on the ground, which from the aircraft perspective, it believed it was on the ground, so it was doing the right thing. It wasn't failing, but unfortunately that led to an accident. So what STAMP does is it fundamentally changes our emphasis from preventing failures to enforcing constraints. And when I say constraints, what I mean by that is we need to enforce, we need to address the behaviours of people and technologies and equipment to make sure that accidents don't result. Now, when we say enforcing constraints, we use what's called a control structure. So you'll notice the square brackets there. You'll notice through a lot of my videos and training, I use square brackets. And the reason I do that is I just want to emphasize I'm using English words, English labels, English terms that mean something very specific in the STAMP literature. Now we'll talk a lot more about control structures later on. Now, when we say, well, what is a STAMP analysis? If somebody says, hey, I'm going to go and do a STAMP analysis, what do they actually mean? Well, there are currently 4 STAMP-based processes, 4 model-based analyses processes. So there is STPA, which is System Theoretic Process Analysis, Hazard Analysis. There is CAST, which we'll be talking about both of these today. Causal analysis based on systems theory, or depending on when you read, what literature you are reading and when it was written, it may also be referred to as causal analysis based on STAMP. That is the accident or event analysis. And then there is what's called STPA SEC, so System Theoretic Process Analysis Security. That is a security-focused version of STPA developed by Colonel Bill Young. He's a great guy. If you get a chance to talk to him, I highly recommend it. And then there is a fourth lesser-known STAMP-based process, which is called STECA, System Theoretic Early Concept Analysis. Now, this was developed by Dr. Cody Fleming. He's not worked at MIT for about 10 years now. He moved on from MIT, but there's not much literature or discussion of what STECA is. But from my perspective, been involved in design and development of complex systems, the Stecker process is very helpful, very beneficial. But I'm not going to talk about that today because it's not really relevant. Okay, so when we say we're going to do a stamp analysis, just to labour the point again, what we're saying is we're going to use the stamp accident causality model, and we're going to do it either during system development or change or during incident or accident investigation. And so when we say what is a stamp analysis, what we're saying is we're going to apply STPA Hazard Analysis as a proactive tool before an accident has occurred, or we're going to apply CAST accident analysis as a reactive method tool. There we go. So STPA then. So STPA, as I said, is an acronym for System Theoretic Process Analysis. What I've done is laid out the way that I teach it. So I teach all the stamp-based methods in 3 phases. So on the left-hand side, we have what I call the foundation phase. In the middle, we've got what I call the modeling phase. And then on the right-hand side is what I call the analysis phase. Now, STPA has 2 parts to its analysis phase. The first part is doing what's called control action analysis. So that's looking at those jigsaw pieces, looking at the controllers and looking specifically at the control actions that that controller provides or not, and then identifies whether they are, whether they will result in an accident or a loss. And then the second part of STPA analysis is what's called loss scenario or causal scenario analysis, depending on which literature you've seen. Now, if we overlay that with what's included in the STPA handbook, the handbook talks about 4 parts to STPA. So the first part, define analysis purpose, that's within the foundation phase. The second part is model the control structure, that is within the modeling phase. And then the parts 3 and parts 4 is control action analysis, and then identify the loss scenarios. Now, the reason I teach it in this fashion is to make it easier for you to grasp the overall concepts of a stamp analysis, whether it's STPA or CAST. But it also means that depending on where you're starting your learning, it'll be easier to start with, STPA and then graduate and use CAST as well. Or if you're using CAST, you can then graduate and use STPA. So I'm trying to make it a lot easier for you to grasp, a lot easier for you to understand. Now, in terms of the basics of the process, so in the foundation phase, which is common to all the stamp-based analyses, is we have what I call the preparation phase. So this is we define the analysis purpose, what are we going to use the analysis for, what is our objective, what are we trying to find, what we're trying to deal with. Then there is the concept or system goals or objectives. So what is the system you're looking at? Is it a new concept or is it an existing design that you want to change? What are the objectives of that system, that design? And then, of course, what is the system definition? So if you're applying this to a brand new concept, you might not even know what your system definition is. And what I'm highlighting here is you don't necessarily need that level of detail to build a control structure model and start generating requirements. And that's one of the powers of using STPA as early as possible in your design lifecycle, because you don't really need a design. It can help you to drive design requirements. So that's and then the first actual part of doing an actual stamp analysis, because these parts you do as part of your existing engineering and safety process anyway, so it's not a huge deal. So you define your losses. So what are the ultimate outcomes or accidents or incidents you're trying to avoid? So typically from a safety perspective, it'll be human injury or death. Maybe it's damage or loss of your equipment or your systems. Maybe it's damage or loss of things in the environment. Maybe it's third-party injury or death. Maybe it's loss of profits or loss of business. And the thing here is you can, depending on the type of system that you're working on, the type of organization you're working in, you could have quite a long list of different types of losses, not just safety losses. Maybe damage to business reputation or trust in the marketplace. Maybe, being really abstract, maybe it could be poisoning the particular pond, particular well of opportunity. So if we're thinking about autonomous self-driving vehicles, If you've got a particular manufacturer in that space that is having a lot of accidents and maybe generating a lot of negative media coverage, poisoning the well is something you might want to think about as part of your system design and your STPA analysis. Then we've got hazards. And you'll notice there I've put the little square brackets there just to emphasize that I'm referring to the definition as used in the stamp literature. And this is subtly different depending on what industry you work in, what domain you work in. So if we're talking about the standard definition of a hazard that most health and safety, that we use from a health and safety perspective, it's typically anything that has the potential to cause harm. And that's such a broad definition that it's almost pointless. Whereas when we're talking about the concept of stamp, we're very specific. We're talking about system states or conditions that will lead to an accident. So it's a much tighter, specific definition of hazard than we're used to. And so if you're doing if you're updating a design, changing a design, you might already have a safety management system with a list of hazards in it, and you'll have to review those and sort of refresh those and define those in the context of stamp before you can move forwards. Then we've got some what are called high-level safety constraints. So these are very high-level safety requirements that directly relate to those hazards. And then the next phase, this is where we get into the exciting work of building a control structure model or models. Now this is, there's quite a lot here, a lot involved in that. It's, you can develop very basic high-level control structure models, as we'll see in a minute, but depending on the scale of the system that you're working on, these control structures can get quite big, and there are some challenges with how to manage those. Now, the output of the control structure modeling activity is two things. You'll have some control structure models of various levels of detail, but you might also identify some architectural constraints, such as you need independent feedback of sensors, sensory information, perhaps. Now the analysis phase then. So for STPA, as I said, there are two parts. The first is control action analysis, and this is where we look at all of those control loops, those jigsaw pieces, and we identify what are the control actions that particular control action can provide, and what are the different ways that control action can be harmful, can lead to accidents. And those ones we identify and label them as unsafe control actions. And of course, if we're doing a cybersecurity STPA sec, we would label the control actions unsecure control actions if that's what we're exploring. And then what we do then is we define what are called controller safety constraints or functional safety constraints. So these are essentially inverting those unsafe control actions into these are the things that the controller must never do. And then the final part of STPA is the loss scenario or causal scenario analysis. And this is where we explore that control loop. We sort of unpick it, look at the different elements within it. How could the controller, how could the control actions, the control path, how could the feedback or the control process itself contribute to those unsafe control actions? And then, of course, what is the contribution from the rest of the control structure? And again, that is quite an involved part of the analysis. And depending how where you are in your life cycle of the project, service or system that you're working on, you will go into a different level of detail. Now, of course, in some organizations, they already have teams of people doing things like failure modes and effects analyses, and the results from an FMEA can be used to enrich the STPA analysis, but they're not a direct read across. Like a fault tree analysis, if you're familiar with fault tree analysis, the starting point, the top event of those fault tree analyses, and the base events and the logic, the gates used in those fault tree analysis will have some parallels to what you find in STPA, but it won't be a direct link across. The logic is quite different in terms of conceptual logic. But we won't go into that today because I haven't got any fault trees to show. And they will probably be classified for an aircraft of this type. So this is the basic control loop, the jigsaw piece I was talking about. And I've highlighted the control actions there. Now, when we're defining the control actions and identifying unsafe control actions, we have a very specific formula for how we define those. So we have a unique identifier, because there could be many of those. Just bear with me a second. There we go, because there could be many of those. We identify the source controller. So if we're talking about the person, if you're driving your car, you are the driver, we'd say driver, and then the specific control action type. So if you're press the brake, provide brake command, and then the specific context. And this is the little bit, I've highlighted this in gold because this is the really important part when you're defining unsafe control actions. And one of the telltale signs whenever you read any of the academic papers by people who've not actually been to MIT and done the been involved in the stamp community or done the formal training with myself or John Thomas, they often forget to include that context. And it's that context that actually defines whether the control action is safe or not. So if you imagine you're driving down the road and somebody steps out into the front of your vehicle and you're driving along and you do not press the brake, you do not provide the brake command, when we're defining the control action, it would be driver does not provide brake command when object in the path of the vehicle. Now, of course, if we're talking about an autonomous vehicle, then that autonomous vehicle needs to have information about the environment. We need to start thinking about sensory feedback and things like that. And of course, if the context of that, somebody is stood in the road, there's an object in the road, but it's not detected by the sensors, then of course that then makes this particular control action unsafe. So I'm not going to go into too much detail on that because we've got a lot to go through, but these are the general types of unsafe control action. So all control actions are broken down into two categories. The first is the control action is not provided when it is required. So if you don't provide the control action when there is somebody in the road, that is a control action that's not provided with that context. But there are other versions of provided. So if you provide, instead of the brake command, you provide the accelerate command with that particular context, is that unsafe? Well, yes, it is. But is there a particular variant of that provided control action? So we've got timing. So we could have timing early, timing late. So if we provide a brake command too late, if we don't provide the brake command long enough, so it's too short or too long. And then also for particular types of control actions, there might be a sequence involved. So if you're thinking about ready, aim, fire, if you're talking about weapons, if you fire first before you're ready or before you've aimed, could that be dangerous? Yeah, probably. And then finally, magnitude. Now, magnitude is a special case that's not included in the official literature, but I always include it on the side just to emphasize that if you're working on a system that has, analog controls or analog feedback, for example, or interactions that involve magnitude, you might want to include that as part of considering your unsafe control actions. But it's, as I say, it's not officially part of the literature. Okay, and then when we're analysing these unsafe control actions, we use what's called a basic unsafe control action table. So we list the control action on the left-hand side, and then we look at the different scenarios. So if this control action is not provided with a specific context, is it unsafe or not? The same for provided, the same for timing and sequence, and the same for duration. And then when we do the control loop analysis, the causal scenario or loss scenario analysis, this is where we look at the different elements of the control loop. So here we look at the controller behavior itself. So why does it make sense for the controller to provide that unsafe control action? What issues does it have with its control algorithm or its decision making? What about its beliefs or its process model? And then also, what about the sensors or feedback? Is the feedback adequate, inadequate? Are there any delays, or is there any other data or information that's missing or incorrect or lying perhaps? And then we've got the control action path. So how does that control action make its way from the controller to the physical control process? What actuators are involved? Perhaps the actuator, provides the control action when the controller hasn't provided the control action. And that's a completely different scenario to if the controller provides the control action, but the actuator doesn't then enact that control action. And then finally, we've got the control process at the bottom. What are the aspects of the control process where it might behave as though it has received a control action or has not received a control action? And of course, are there any other external disturbances that are not directly related to this control loop? And then in terms of results from hazard analysis, we've got the high-level safety constraints I mentioned earlier on, the control structure architectural constraints, the controller functional safety constraints, and then the safety constraints for the control loop and the feedback and the sensors and actuators, things like that. And they're broadly labelled as stamp-based analysis constraints, if you're doing an STPA. So they're constraints. But we have to translate those into the system requirements set if we're talking about an aircraft or a weapon system of some description. And they will be put into buckets. Some will be clearly safety related requirements, some of them will be actual formal safety requirements, and some will be functional, non-functional requirements. So there's quite a mixture there. So CAST, we're going to jump in and talk about CAST now. So CAST is an acronym, again, causal analysis based on systems theory, or STAMP, depending on what vintage of literature you're looking at. As I mentioned, it's 3 phases again. You've seen the first 2, so the foundation phase, the modelling phase, and then we've got the analysis phase. So this is where it's a little bit different to, we've got somebody else joining us. There we go. There we go, so we've got someone else. Fantastic. So the analysis phase has 3 parts in this case. The first is the physical process analysis, the second is the controller analysis, and then the third is the control structure analysis. So when we're doing the physical process analysis, this will be very familiar with you already in the stuff that you already do, because this is where we look at the physical components, the actual things that are involved in the accident. So, what are the components, what happened? Let's list the physical equipment, physical processes and controls, including so-called barriers, physical barriers. Then we've got the roles and responsibilities for those physical components. Are they hazard mitigations? Are there any safety requirements related with them? Any safety constraints? And then whether there were any physical failures or physical issues. So in the case of this accident, we know that the landing gear struts, they had contaminated hydraulic fluid in there, and because of the contamination, it's believed that they froze, and that contributed to the landing gear struts not returning to where they needed to be, the oleos, and that contributed to the weight on wheels, giving a false indication to the flight control system. And then, of course, any contributory control actions or unsafe interactions. Now, it's important to note that at this stage, we're not talking about people or control systems. We're not looking at that at this stage. We look at those in the next 2 parts. Now, of course, we have to identify and document reasons how or why, what are the explanations for those issues with the physical process. Is there any missing elements missing or flaws or inadequacies? Is there any specific context or contextual factors? In our case, temperature, environmental conditions were certainly an aspect. And then a summary of that contribution. What is the role of those physical components in the accident? And then we document any questions or recommendations, recognizing that, this is not a sequential process when we're doing an investigation with CAST. We don't do the physical process first and then controller and structure. You're probably going to have a team of people working on this. You're going to collect evidence that's going to be physical, of course, so you might want to do the physical analysis first, but it could be sequential, it could be overlapping, it could be in parallel. And you might identify questions and make recommendations that as you start to learn more about the control structure and the behavior of certain controllers, that might change those questions, might answer those questions, or the recommendations you might make then become invalid later on as you progress through the analysis. And then in terms of the second and third part of the CAST analysis phase, we have what's called in the literature component analysis or controller analysis, because we're looking at the controllers in the structure. We identify what safety-related roles and responsibilities they have, any explicit safety requirements or constraints. We'll then explore their control and feedback ability. What are the issues? Were there any issues with actuators and sensors? Were there any failures? So, we're looking at the controller and, actuators and sensors perhaps. Then we've got contributory control actions or interactions. And you'll notice that this is different from STPA. We're logically talking about exactly the same control actions and whether they contributed to the accident or not. But of course, when we're doing an STPA, this is before the accident. So, when we identify a control action that will lead to a loss, that is clearly an unsafe control action. But in the context of a real accident, you might have a situation where a controller provides a control action, believing that it is the right thing to do, the safe thing to do, but that actually contributes to the accident. And of course, they wouldn't know that it contributed to the accident before they did it, because if they did, with hindsight, they would not have logically done that. So this is why it's important to recognise that contributory control actions in CAST and unsafe control actions in STPA are logically and functionally the same, but we just have to be careful about how we treat them post-accident, because we don't want to suffer from hindsight bias. We want to reduce the potential to be overwhelmed by hindsight bias. Then we look at the reasons how, why, or what the explanation is for why those contributory control actions were provided or not. Then we look at the actions, behaviours and decision making. So what decisions did this controller did the controller make? What mental or process model issues or beliefs existed? What flaws did they have? In this particular accident, the flight control system believed the aircraft was on the ground when it was actually in flight, and that is, then that led to it applying the ground control laws, which clearly led to uncontrollability, inadequate controllability of the aircraft and ultimately loss of the aircraft. And then contextual factors, and then summarise the role of that component in the accident, and then document any questions and recommendations. And then the final part is the structure analysis. So this is where we actually explore the control structure itself. We look at various elements of it. So we've got communication and coordination, we've got structure and architecture and interactions, we've got dynamics and changes, and that could, or evolution, and that could be whether the product, service or system itself. It could be the environment that system is in. It could be the organisation and humans themselves, including behaviours. So they may become complacent over time. They might perceive things differently. And then, of course, planned or unplanned changes, and of course, unofficial or official changes. They might contribute to things. And of course, we can also look at work as imagined versus work as done. So if you model the control structure as it was in the accident, and then explore the same control structure or model the control structure as work was imagined, the differences in those two control structures can represent why the accident occurred or contributed. We've got a single source of information in this case, which is the official accident investigation report from the US Air Force. It's 39 pages, so it's not that big, and it was produced less than 6 months after the accident, less than 6 months after the accident occurred. So they were doing this pretty rapidly. So we have to bear that in mind. And of course, I was made aware of this from the Warzone article with the sort of, incendiary headline, I suppose. Dramatic F-35 crash at Alaskan Air Base caused by iced up landing gear. So very simplistically, I suppose it is caused by the ice up landing gear, but what else is going on there? That's what we're going to explore. So ice in the F-35's landing gear led the jet's flight computer to think it was on the ground when it actually wasn't. Now, in terms of just a bit of context then, so this was at Eielson Air Force Base in Alaska, US. It was Tuesday, the 28th of January, 12:49 local time. The weather conditions, visibility was 15 miles, winds 260 at 4 knots, so it's not very windy. The cloud ceiling was at 4,500 feet above ground level, so relatively low. Temperature was -1 Fahrenheit, which is -18 degrees C. Dew point was -5 Fahrenheit, -20.5. There was no significant weather with freezing level at the surface, and then at 10,000 feet mean sea level, above mean sea level, forecasted -29. So for somebody like me in the UK, that's pretty cold. So it's kind of hardly surprising that I'd have issues with icing in contaminated hydraulic fluid. And this was a US Air Force Lockheed Martin F35A flying from Eielson with one pilot on board. So just in summary then, for those that have not read the report, don't know the details, this was an F-35A conventional takeoff and landing Lightning II aircraft, a modern fast jet advanced aircraft, crashed after completing a touch-and-go landing on runway 32 at Eielson Air Force Base. The pilot ejected safely before aircraft impacted the ground, suffering minor injuries, so they were very lucky, as were the other people on the ground, because this was a busy airfield with a lot of big aircraft doing a lot of big things, and if this aircraft had come down on top of those, that could have been very, very serious. Contaminated hydraulic fluid froze in the nose landing gear and main landing gear struts. Ice prevented the landing gear struts from fully extending after the aircraft lifted off. The weight on wheel sensors indicated aircraft was still on the ground when it was actually airborne. The aircraft flight control system transitioned into on-ground flight control law. 3 out of 5 weight on wheel sensors agreed, leading to an aircraft controllability issues. The aircraft was destroyed upon impact with the ground with a total loss of $196.5 million. So it's quite a big, expensive accident, this one. And again, you've seen these two pictures. These are representative of the aircraft that was lost. So what I'm going to do now is, what questions do you have before we get the Miro up? What are your thoughts? I think everybody's quiet. Either I'm doing a great job or I'm not. Let's move those things out of the way so I can see what's going on. So Aidan said something. There we go. Let's get that on screen. Aidan says the hydraulic barrel was left outside in inclement weather for at least 6 weeks. This was in direct violation of Air Force regulations, which require that hydraulic fluid be stored in a container tightly closed in a dry and well-ventilated place. Additionally, the hydraulic barrel that was used to service the MISAF aircraft had been marked empty consumed in April 2024, but had not been disposed of. Even so, it was in use and when tested contained about 33% water. So that's, in a nutshell, that is the cause of the accident. But there's more to it than that, and we will see that as we go through this case study. So let's go to this bit. Slides, large. No, that one. There we go. Give me a thumbs up or tell me in the chat whether this is big enough for you to be able to see. If you can read it, I'll make it a bit bigger. There we go. Got some thumbs up. Fantastic. Thomas has added something. There we go. The touch and go landing, in hindsight, was questioned. Some thought that the aircraft would have gone better off simply landing on that touch and go. Yes, absolutely. And there was a second accident a few weeks later. Or sorry, not an accident. A similar situation occurred with another aircraft a number of weeks later. That the investigation report talks about, and we'll come back to that because it's quite interesting. It sort of indicates some beliefs on the part of the investigator, which I think are a bit unfair, a bit hindsight biasy. Jose, we've got did not have time to study it, but weight on wheel sensors, and claw called my attention. Absolutely. Okay, so what I've done here is, if you've seen the videos at all, essentially what I did was just went through the official investigation report with a marker pen, just sort of underlining things, talking through it, and essentially worked through it over the course of about 5.5 hours over sort of 2 or 3 days. And essentially, as I went through it, what I did is I extracted relevant information that I thought might make sense for the control structure, bearing in mind that when you're doing the if you're doing this as part of a real investigation, if you are the investigator, you will receive notification that an accident has occurred with some initial information, which is pretty much always going to be wrong. And of course, when you're starting your control structure, you will identify candidate controllers that might or might not be relevant to this accident and whether you want to include them in the control structure. So what I do is I just identify them as jigsaw pieces and put them to one side. And then as I get more information, I will then take those candidate controllers and start arranging them in a broad hierarchy and then see what the interactions are, what the control actions and feedback are. James has made a point. Hydraulic fluid is hygroscopic, So why is ice formation with contaminated hydraulic fluid a surprise and not checked at every service? That's a fantastic question. That's not addressed in the investigation report. James says its text is hard to read. Yeah, sorry, James. I was just quickly going over the report itself, just quickly to give you a view of what it looks like. So not sort of detailed of it, but I'll just... so this is the layout of the airfield. Well, I can't remember where the impact location is. I think it's... where is it? Oh, no, that's not it. I thought they'd marked it on this. Maybe it's marked on a different one I've seen. But that's the overall runway layout, airfield layout. Then we've got... Oh, there we go. There's the picture I was thinking of. So this is the airfield layout, the aircraft impact site. I can't zoom in any further than that, unfortunately. But the blow up of this, you can see that that's the main runway. This is the aircraft impact site. And then literally over the other side is a parking ramp with lots and lots of other aircraft, including some big tankers, air-to-air refueling tankers. And I'll quickly, in fact, actually, while I do this, I'll quickly show the video. So let's just click on that one. You should be able to see this. I'll blow it up a little bit. Yeah, so it's quite an extreme thing to witness. When I first saw it, I was shocked. I mean, the first thing that struck me is, why is it falling out the sky, tumbling down? There's something wrong with the flight control system if it's doing that. And you can see these large aircraft, these are air-to-air refueling tankers. So if it had come down the other side, it could have been very, very, very expensive. Not just very expensive. There we go. So that's that picture. Now, with that in mind, just for a moment, I'm going to plant a seed in your mind, and I'm going to show you another video. But this video is of a different type of F-35. This is an F-35B, vertical takeoff and landing. So you notice it's touched down, and then it immediately pitches forwards. Sorry for the swearing. And then they bang out, fortunately. Yeah, so the reason I'm highlighting this one is just what we're about to do in this case study is relevant to this one, I think. They're not going to be exactly the same flight control systems, of course, because they're different marks of aircraft. But I just wonder if there's some similar architecture questions that the manufacturer might want to consider. So as it's coming into land, you can see the landing gear compressors, leaves the ground, and then immediately tips over. There we go. So I just wanted to sort of show you that and plant a seed in your mind. So yeah, so what else were we looking at? Okay, so yeah, so there is an example of the contamination in the nose landing gear and the right main landing gear. So this, the brown stuff is the hydraulic fluid and the clear stuff is the water. And you'll notice there's a third of water in there. That's not good. That's not what should be going on there. So yeah, and then we go across to this picture here. This is a bit of a better picture. This is the nose landing gear fluid. And then this is the main landing gear fluid. Again, it's not good at all. It shouldn't be like that. And then this is the barrel. So this is the hydraulic barrel, and you can see for yourself, the barrel is in a bit of a poor state. There's surface corrosion, paint chips. It looks like it's been banged up a bit. And then this thing on the top, this is a hand pump to dispense the fluid out of the barrel into the maintenance cart, the hydraulic servicing cart. And the thing that I've highlighted there is that the threads on here, they're supposed to be sealed so that when it's in the barrel, there's a watertight seal. For whatever reason that's not explained in the investigation report, that's not present. And then this is... well, pretty much a week or so later, there was actually another incident on the 6th of February. 9 days later, there we go, yeah. So 9 days later, another F-35 took off, experienced a landing gear malfunction on takeoff. That aircraft experienced a nose wheel gear unsafe indication after takeoff, and following the gear failed to retract checklist, the pilot lowered the landing gear and flew for approximately 40 minutes before landing uneventfully. So this was a near miss where nobody got hurt, nothing was lost. Now what's interesting about this one is the nose wheel landing gear was canted off to 10 degrees. And when they attempted to land on touchdown, it moved to 5 degrees. And fortunately, that didn't result in the aircraft departing the runway or flipping over. And the pilot nor the wingman noticed the nose wheel was canted prior to the uneventful landing. So they didn't even know. Their mental model was they didn't know there was an issue with the landing gear. So they were, in my view, they were very lucky, I think. And that aircraft, they also checked the contamination and found that the nose landing gear and left main landing gear was contaminated, but the right main landing gear was not. So this is a common mode of losing aircraft potentially. Now, in terms of the landing gear mechanics and everything, there's not really much to say about it, really, other than that it was affected by the cold, the frozen hydraulics, so it didn't compress properly. Actually, there's a better picture of the landing gear. So this is the nose landing gear, and this is the right main landing gear. And you can see there the oleos themselves, and they compress when the aircraft touches down. These are the weight on wheels sensors. Now, there's a difference between the nose landing gear sensors and the sensors on the main landing gears, in that the nose landing gear sensor is a weight off wheels sensor, not a weight on wheels. So the logic that it provides to the flight control system is that we are off wheels, we're not on the ground, whereas the main landing gear is 2 sensors per landing gear that says that there is weight on the wheels. Okay, all right, what else can we say? Yeah, there we go, there's a better picture. So these are the 2 sensors there, and when the landing gear mechanism moves, they press the weight on wheel switches and they indicate weight on wheels. And there's the nose landing gear there. So it's a Hall effect sensor, and it's about weight off wheels, not weight on wheels. Right, okay, so let's go over to here then. So this is, like I said, I always start with this jigsaw piece. So whenever you're doing any kind of stamp-based analysis, start with this jigsaw piece and build up from there. And then think about putting these pieces together into a control structure model. And so in the case of the pilot, I essentially started at the front of the investigation report and started to pull out what controllers were involved, scribbled them on here. That gave me a preliminary idea of what the control structure looks like and what the potential unsafe interactions are. And then also I did the same for the maintenance of the aircraft. So the hydraulic, putting hydraulic fluid into the landing gear using the hydraulic service handcart, which is filled up from a hydraulics barrel. Excuse me. But it wasn't clear in the investigation report who else, apart from the maintenance team, a level 5 and a level 7 maintainer. There were other people, implied but not actually mentioned or apparently investigated. There was a mention about the 355th hazardous communications. Is it comms? Yeah, hazardous communication support program manager, who wasn't in post. There was no one in that position. So arguably that part of the control structure, there was nobody present. So it's hardly surprising that there were some issues. So I essentially redrew those a bit smarter, a bit nicer. It's a bit more complex because I've added some detail to it. I can, as I mentioned before, when you're doing your control structure modelling, it's a good idea to start with a very basic control structure, 3 boxes with a couple of arrows, nothing more complex than that, and then start to add details. You learn more as you start to understand more, and you go through a bit of a, iterative phases of, adding detail and removing detail and refining it until you have a good control structure model that you can use for the basis of your analysis, and of course communicating with others. Because when you're doing your own stamp-based analysis, you want a master model that captures all the information that's relevant to you. And then, of course, when you're going to write this thing into a report or put it in an investigation report for other stakeholders to either review or to consume, if you're going to publish a report in public, you're not necessarily going to want to publish your detailed control structure model because it's sensitive. You will want to publish something that's a bit more abstract. So you have to think about how you're going to go about modeling it. And it's not straightforward. It comes with time and experience. But once you develop that skill, it'll become second nature. So what I've got here is I've started with the physical process, which for this whole accident is about aircraft flight trajectory. Because ultimately we're talking about an aircraft that needs to fly, complete its mission, whatever that is, return to base and land safely, and everyone gets home safely. Now the flight trajectory as a physical control process is influenced by the flying control surfaces. Now I've not included the propulsion system, the engine or anything to do with that because it's not discussed in the report and I'm not convinced it's relevant to this particular accident because it's not. If we were talking about the F35B vertical takeoff and landing example that you saw the video of a moment ago, of course we might want to include that in this control structure, but we're doing it for this accident, not for the F35B. So the flying control surfaces, they are under the logical control of the flight control system. Now the flight control system has, the same control algorithms, decision making and beliefs process model as a human controller, but in this concept it's more appropriate to refer to them as control algorithms. And in fact in the investigation report it refers to them as control laws or claws. Now it mentions explicitly three types of control laws, algorithms. So there's the up and away, the power and approach, and then the on-ground control law. Now the report talks about the weight on wheels sensors. So I've modelled them explicitly. You don't have to do that. I've just done it for the effect here. So we've got the nose landing gear, we've got the weight on wheel sensors, and I've highlighted the nose landing gear is a weight off wheel sensor. They provide critical feedback to the flight control system. That flight control system updates its process models about the state of the aircraft, whether it's in the flight or on the ground. So it believes, based on this apparently valid information, 3 out of 5 voting, that it is on the ground when in fact it's not. And so it selects its decision making, its algorithm decides, based on that belief, that process model, that it needs to enter into on-ground mode control laws. And it does that, and when it does that, it starts moving the flying control surfaces as though it is on the ground, which if the aircraft is in the sky, that's really not appropriate. It leads to an uncontrollable aircraft and a loss of $196.5 million. So fundamentally, straight away, from an aircraft perspective, we've identified the causes of the accident. It is unsafe control actions by the flight control system because it believed the aircraft, legitimately believed in its context, that the aircraft was on the ground. So there's an immediate question there for the designer of the flight control system. Why does it make sense for the aircraft to select on ground when it's actually in the air? What other feedback do those process models, do those beliefs have about the state of the aircraft to protect it from this precise scenario? Now, of course, they're not going to include that level of technical detail about a fighter jet, a military system in a report like this because it's a publicly available report. But if I was part of the investigation team, and I'm hoping you all now as part of the work that you do, you'll be able to ask questions about, well, hang on a minute, what feedback updates this beliefs process model? And do those false beliefs contribute to unsafe control actions on the part of the controller? And if they do, have we got a design issue here? Do we need more feedback to give us confidence that we're actually in the state that we are? Maybe we might also want to consider aircrew override capability. Can the pilot flip a switch that says we're definitely flying, we're definitely not flying? I'm just postulating there, but I'm hoping. In fact, tell me what are your thoughts about this? I can bring you up and we can talk about it. Just type in the chat or raise your hand and I'll bring you on. Jose says it reminds me of Air France 447. It is. It literally is. I should probably do an Air France 447 case study, but it's such a huge investigation report. It'll take absolutely ages to get through. But yeah, for me, looking at the summary of that accident, this is similar. But in that accident, it's also related to the crew. So the crew were led to believe that they were not in the state that they were because of the feedback from the aircraft. So there was not only a control system flaw from the flight control system perspective, there was also a flaw in the human-machine interface design of that aircraft. Any other comments, questions, concerns, compliments? I'll keep going up the controls. Oh, someone else has said something. James said something. There have been several other accidents where there has been similar mismatches involving WOW. Yes, there has. Absolutely. WOW is particularly problematic. How much can I say? I've been involved in some analysis of WOW-related fault tree analysis about 5 years ago now. Yeah, maybe 5 or so years ago. And it's not an easy thing to do because in that context, I was doing analysis on the part of a subsystem supplier. And so the aircraft manufacturer, they did their analysis and their fault trees and they decided their architecture for the weight on wheels system. But when I was doing the work and doing a bit of pseudo STPA in combination with fault tree and FMEA, I identified that perhaps their signal to us was not of sufficient integrity for the benefit of the functions, safety critical functions that we were working on. And of course that suggested that the aircraft design for the weight on wheels signal was not adequate. But of course we didn't have full visibility of the aircraft manufacturer's architecture for that design. They only gave us a limited amount of information in the interface control document. So I mean, in this case I've not explicitly discussed the design control structure for the aircraft. And in fact, that is something we should probably talk about now, actually. Ruben, I think you mentioned that. Ruben, are you still here? Ruben, you asked about... There we go. Let's have a look. So Ruben says... there we go. Probably not mentioned on the public report. But looking at the FCS flight control system software designer's mental models as a controller of the flight control system would probably shed more light on the causal factors. Absolutely. I mean, of course, in this context, the only information we've got is in the official investigation report. But amongst the people in this room, I'm sure we can sort of come up with some ideas as to why would it make sense for the flight control system designer and their software engineers to design their algorithms in the way that they are. It may literally be the flight control system software engineers were told, hey, these are the up and away, power and approach and on-ground algorithms. This is the only available feedback to you because of other constraints on the design of the aircraft. I don't want to... Let's play devil's advocate a little bit. Maybe, and I don't know how this works. I think someone else in the call knows a lot more about landing gear than I do. But if you're buying the landing gear from a supplier and that landing gear supplier says, well, this is our standard landing gear for a fighter jet of this performance and these requirements, it only comes with weight on wheels of this design. If you want more than that for the benefit of your flight control system, you need to give us $10 billion or whatever it is. Then maybe that's the reason that, or it could be that, and we can't know, but I would guess there may be other flight control system reasons why they can't do that. Maybe it's... I don't know, I can't... Well, let's say for argument's sake... in fact, actually, I drew it. I wrote it. There it is. That's what I wrote. Yeah, so I said, well, what about adding G loading? Because if you're on the ground, I'd like to think the G is going to be relatively stable depending on how hard you hit the ground and how much wobbling you do on the ground when you come into a stop. But if you're moving in air, you're going to have a greater variance with smoother performance on the curves of G. What about airspeed? If your airspeed is above 250 knots or whatever it is, clearly you're not on the ground if you've got an airspeed of 250 knots. And I know for a fact that the airspeed is going to be a high integrity signal, high integrity data from multiple sensors on board the aircraft, probably diverse sensors. And then what about altimeter? Is there any altimeter data they could use? Or is there a radio altimeter data they could use? I know in some civil aircraft designs, I think Jose mentioned it earlier on. James mentioned it. There are other accidents with things like thrust reversers, where the aircraft has believed that it's in flight when actually it's on the ground, and the pilots are trying really hard to get the thrust reversers to work when it's heavy rain, the aircraft's heavy and it's windy, and the thrust reversers have not deployed. They've departed the runway and killed everybody. So, weight on wheels is a critical thing, but what other elements, other feedback could the designers include? Or maybe they attempted to include it, but for other reasons they couldn't include it. I don't know, but that is certainly something I, as an investigator, would want the team to go and look at, to explore. So Ruben says yes, +1. James says, in order for the aircraft to have left the ground after that touch and go, the at least part of the flight control system must have been aware that the aircraft, the only way we'd know that, James, is if we had someone who knew about this flight control system, but then this meeting will be classified. But yeah, absolutely, that's it. What else can I say about that? So going back to this one over here, so I've just modelled that very basically. That, for me, that is the key to this accident. If we then move up the control structure, there's some other interesting points. So the mishap pilot, they interact with the aircraft through some flying controls, so they provide inputs to the flight control system. I am assuming that the flight control system gives them some kind of feedback. If you're familiar with Airbus aircraft with twin pilots, commercial aircraft, Jose mentioned Air France 447. So they have, they're not like Boeing aircraft. Boeing aircraft, some of the older ones, pilots can actually feel on their control column that their second pilot is actually moving as well. Whereas on stick-based controllers, like on the Airbus aircraft, you can't actually tell whether there's people putting multiple inputs in. I think they do come up with an alert that says, hey, the other person's trying to, provide stick inputs and they have to coordinate their control. But yeah, that's, that from a feedback perspective on the flying controls, I'm imagining the F35 has some kind of feedback to the pilot. They also have the panoramic cockpit display and the helmet mounted display, and I've modelled them here as feedback paths to the pilot, and clearly they update the beliefs and decision making of the pilot about what they're going to do about the aircraft. I've also modelled the mishap wingman, because clearly they had, in fact I'm missing a feedback loop from the aircraft there. I should have a feedback path from there to the wingman, because clearly they're the person that spotted that there was an issue with the aircraft. So I've just added that on there. I mean, if he'd not spotted those issues, like in the second near miss that they had 8 days later, things could have been a lot worse for that second. It could have been a lot worse for this pilot. Then we have the supervisor of flying. They interacted with the 354 operations group leader and the conference hotel, which was a conference call while the aircraft was still in the sky with the manufacturer. So they had a team of people which were on the call giving advice and doing fault finding and recommendations for the mishap pilot. Now, if I go over here, where is it? There was actually a landing gear subject matter expert, 3 of those. There was a software engineer and a flight safety engineer in that conference call. Now, one of the things that's interesting about this that's mentioned in the report is they were not aware of a maintenance letter that was issued 6 or so months prior that actually highlighted an issue such as this, but they weren't aware of it. They didn't realise that issues such as this could lead to loss of the aircraft. Now, it's important to recognise that this maintenance letter was published in the months prior, but they didn't emphasise that issues of this nature could lead to loss of the aircraft. They just implied it might lead to controllability issues. So anybody reading that anyway would not have realised, hey, this is actually going to lead to loss of the aircraft. We need to do something serious here. The other thing to emphasise is this conference hotel did not have any flight control system competent people in the call. So they'd not identified that this might lead to loss of the aircraft. They'd just assumed it was a standard landing gear issue and they could have a go at landing, and if they can't land, then they're probably going to have to eject. It doesn't appear to, from what's in the investigation report, that it actually related to a potential for loss of the aircraft. So there's questions there over, well, who designed this thing called a conference hotel? Who decided who the people should be in that room? How was that designed? How was that part of the control structure actually set up? And it's important to emphasise that the mishap pilot was coordinating with this conference hotel via the supervisor of flying, talking to them on their personal phone. So even this was it was a phone call. It wasn't like a high integrity data link with live data or telemetry or anything like that. It was just a phone call. Hey, we've got this $200 million fighter jet flying around with problems with landing gear. Can you just give us a hand, please? So James says, I say that simply because it managed to defeat gravity and get some considerable height before the pilot had to eject. The idea that it managed to use residual speed or other magic to get that high is a bit far-fetched. I think, if I recall correctly, the investigation report talked about the pilot essentially trying to take off again, and then almost immediately after takeoff they lost control of it and it ascended to a significant height before it then came back down again. I think it's in this part actually. So second touch and go. So after further discussion on the conference hotel between the supervisor of flying, a senior 354 OG operations group leader and Lockheed Martin engineers, the decision was made to accomplish a second touch and go at a higher than normal speed. So if we go back to over here, when my computer wakes up, there we go. So this conference hotel, they made a decision using an unspecified control algorithm in the investigation report to decide it was safe to go and attempt a second touch and go. So logically, their beliefs must have been, there's no issue with the flight control system and the landing gear system that's going to lead to loss of the aircraft. If they had believed that, if they had an accurate belief, mental model, then they might not have suggested a second touch and go. And again, that's the maintenance newsletter there. Had they been aware of that maintenance newsletter, perhaps they might have made a different decision. And that's what the official investigators concluded at the end. Basically, well, if they'd have known that this maintenance newsletter existed, they might have made a different decision, which in hindsight, it's not fair to say that. And again, the maintenance newsletter was not emphasising how serious it was. So in fact, I'll just jump back over to the maintenance newsletter over here. There we go. So Lockheed Martin released a maintenance newsletter in 7 months earlier that discussed main landing gear weight on wheel switch faults. So it's focused on switch faults, not on flight control system logic. So the WOW switches on the main landing gear are a mechanical plunger switch that are known to have a history of failure due to internal damage. So this is about the failures with the weight on wheel switches themselves, not related to this scenario, which is the switches were working fine. It's just the landing gear wasn't, decompressing properly. These failures assert as actionable health reporting code issues and become more frequent during extreme cold weather operations where aircraft are prepared for flight in a climate-controlled hangar and take off 20 to 40 minutes after being exposed to outside ambient conditions. Faults should be taken as early indication of failure. So if the people involved in the accident were aware of this, they might have assumed that it was an issue with failures of the sensors themselves, not that the sensors were working and it was something else. So in terms of beliefs, mental models, that might explain why they suggested to continue what they were. They might have believed it was just weight on wheels failures, switch failures. In an actionable HRC health reporting code if an actionable health reporting code is asserted noting a fault to a main landing gear WOW switch, the anomaly and failure resolution system tied to the HRC must be followed, and not acting on a WOW switch fault HRC could result in WOW switches failing on a future flight which can cause erratic flying qualities, making it difficult for the pilot to maintain control of the aircraft. So, if we have faults with the switches, it might cause erratic flying qualities. That's not quite the same as it'll cause the aircraft to become completely uncontrollable and crash in the airfield and nearly kill the pilot. But again, this is about switch faults, not necessarily about flight control systems or other reasons why the aircraft might believe legitimately that it's on the ground when it's actually not. And also this AFRS, Anomaly and Failure Resolution System. I don't know what that is. It's not discussed in any detail in the investigation report, but I've just highlighted it. Let's just move across over here. I highlighted it there because it's near to the... It seems to be relevant to the beliefs and decision making of the conference hotel, and it might be relevant to the pilot, but there's no detail. I can't comment on that. But if I go back to this one over here, I just simply put it on there. There's no control actions or feedback because I don't know the detail. If I was doing the investigation, I'd ask questions about that. So we talked about that. James... sorry, James. So the aircraft... where is it? This bit. So the mishap pilot acknowledged the... No, it's not that one. There we go. So this time the mishap pilot would briefly touch the nose wheel down to the runway, take off again, and the mishap wingman would do a battle damage assessment to see if the main mishap aircraft nose landing gear centered. So it's good that they had two aircraft flying together and they had enough fuel and the weather wasn't so bad they couldn't do this. So this was perfect conditions for this. We should learn so much from this. The mishap pilot acknowledged this change of, what was it, COA? I can't remember. Course of action, there we go, that's it. The mishap pilot acknowledged this course of action and proceeded to the visual flight rules entry point Sally to accomplish the second touch and go via a straight-in pattern. Now notice the times on this before I quickly go into it. So 21:48 and 15 seconds, 21:48, 44 seconds. So 30 seconds between is flying okay and bang is on the end of a parachute descending to the ground. So the mishap aircraft main landing gear touched down, followed by the nose landing gear, 24:48, 21:48, 18 seconds. The tactical forward-looking infrared, is it T-FLIR? I can't remember. Video from the mishap wingman showed both the main landing gear and nose landing gear touching down on the runway. Once this occurs, the T-FLIR video and crash survivable memory unit data showed the nose wheel went from 17 degrees left to 6 degrees left when it touched down. At 21:48, 19 seconds, so 1 second later, the mishap pilot momentarily selected maximum afterburner. Right, okay, so your question, James, the idea that it managed to use residual speed or other magic to get to that height is a bit far-fetched. The answer to that is because the afterburner was on. And the mishap pilot lifted back off the runway at 21:48, 24, so 5 seconds after touchdown. At 21:48, 32, an FCS flight control system engine reset was initiated by the pilot, so they provided a control action to the aircraft. And at 21:48, 36, 4 seconds later, when the mishap aircraft is climbing away, the mishap aircraft began to experience significant oscillations in the yaw axis, followed by oscillations in the pitch axis. The mishap pilot attempted to counteract the oscillations with the control stick before selecting max ETR. That's max afterburner. At 21:48, 48, 41 seconds, so 5 seconds later, so 5 seconds wobbling around. At 21:48, 42, the mishap pilot attempted to initiate a left bank, at which point the mishap aircraft rolled to the left aggressively and pitched up. The control stick inputs were neutralized at 21:48, 43, indicating the mishap pilot released his hand from the stick. At 21:48, 44 seconds, the mishap pilot jumped out, banged out, black and yellow. Testimony from the mishap pilot reinforced that the mishap aircraft experienced uncommanded yaw and pitch oscillations. So these are, if I just quickly jump over here, these are not control actions by the pilot because they released the stick. So it must have come from either the flight control system or an external interference, which is not discussed in here. So it must be the flight control system that's done this for the reasons we've already discussed. Where is it? So we got back to here. So the mishap pilot attempted to counteract those movements before attempting to turn the mishap aircraft away from the populated area of the airfield and ejecting. So they were very brave to do what they did. That's just, they deserve a recognition for that. According to the Crash Survivable Memory Unit, the ejection was commanded at 21:48:44. The mishap aircraft was travelling at 222 knots and approximately 372 feet above ground level, with the mishap aircraft at 30 to 40 degrees pitch up, minus 38 degrees left roll, and approximately 3G. So, thank you to Martin Baker ejector seats for saving that person's life. I'm assuming it's Martin Baker, so well done. Okay, right, what else have we got there? So Adrian says, not aware that water in the hydraulic fluid would cause a problem. Okay. Well, let's jump over here to talk about the... so this is the scribble I did the other day about the hydraulic fluid, and I've made a nice clean one over here. So this is the aircraft here. You've noticed I've put these nice little red lines in there just to emphasize that this other control structure is interacting with those three parts of the aircraft. I wouldn't conventionally do that if I was doing it formally, but I'm doing it for the purpose of being able to talk over the top of it. So you can see these red lines, they go all the way over here, and they represent this control process here. In this context is the mishap aircraft. The mishap aircraft is under the control and influence of the maintenance team. As I mentioned, there's a level 5 and a level 7. They made some decisions. They were told to do some servicing. They were required to do servicing, so they did some servicing. So this control action is provide some servicing. But of course, the provision of that servicing was in the context of they're using contaminated equipment, contaminated hydraulic fluid. So the question there for their mental model, if I was doing the investigation and interviewing them, say, hey, ladies, gents, why did it make sense to use this hydraulic fluid? Why did it make sense to use the equipment in the way that you did? And they'll probably say, I'm playing devil's advocate, they'll probably say, well, I didn't know it was contaminated fluid. Well, the investigation should establish that, but let's imagine that they've come to work to do a good job, not hurt or kill anyone. If they knew it was contaminated, I'd like to think that they would not service the aircraft with contaminated fluid. That's always a possibility. So when we're doing a safety investigation, we have to always be open to the possibility that there is some hostile actions, threatening actions, but, generally as part of a safety investigation, we don't assume that, but, there's always a possibility. So let's say that they're good people, no problems there. So they must have believed logically that it was safe to use, that it wasn't contaminated. Well, why is that belief then? Well, perhaps, maintenance supervision has said, hey, you need to use this hydraulic service handcart to do this maintenance. And they've either not got the responsibility or didn't know that they needed to check whether that hydraulic service cart contained, contaminated fluid or not. Maybe they've assumed it's not contaminated because they believe that the control structure around them is functioning properly. Now, the investigation report doesn't say who or what is involved in looking after and making sure the hydraulic service handcart is actually appropriate for the aircraft. There's no discussion of that. They also mentioned the hydraulics barrel and the control of that. They mention a log. I've highlighted log twice because there's two different logs. One is about the hydraulics and one is about maintenance itself. And I've highlighted those orange and not added any detail because there's nothing in the report. What I'm saying is the log itself is not a controller in the conventional sense because it doesn't have the ability to make decisions or enact control actions, but it is a type of process model because a log is essentially a record of the state of the control process, and that record is used by a controller to inform their beliefs, their process model about the state of whatever control process it is. So this log here, this is supposed to maintain a record of what that barrel contains, when it's been checked, where it's been stored, all of that good stuff. And of course, that should be used by somebody, we don't know who, to actually make sure that that barrel is not contaminated. And then, of course, we've got the the pump and the refilling activity of that barrel. And we mentioned earlier on, I'll just quickly jump back to the picture. We mentioned earlier on that it wasn't sealed, apparently sealed properly, if that's the case. You know, I don't know if I'd imagine that it should have a seal on it, but I don't know what the procedures or detail are because it's not discussed in the report. It's kind of hinted at. So if we go back over here, so who's involved in fitting the pump and the refilling the barrel? You know, what was their beliefs? You know, did they believe that they were supposed to not fit, you know, that seal in the way that they did? Who's checking that? Is there a double check? Does somebody check that? Is the double check, hey mate, have you done this? Yeah, I have, mate. Done. Or is it, have you done this? Yes, I have. Great, I'm going to inspect. Oh no, it's not been done. That's a different kind of double check. And actually double checking and the control structure that supports a double check is a common issue across literally everything. You know, the patient safety work I do with medication and dosing and, you know, creating a prescription, defining a dose, dispensing medication and then giving it to a person, administering it to a person. There are checks all over that. But if the checks are not architectured properly, if the control structure doesn't support it, you can end up overdosing somebody. The same with the railway switch example I did and put on YouTube the other week. The massive 4.5-hour video. That's just basically an accident to do with a switch that's left in the wrong position. But there's so much that I tore out of it by looking at it through the lens of CAST. And then, of course, well, who or what is supervising this maintenance? Why was that dysfunctional? We don't know. The investigation doesn't talk about it. The only thing it really talks about is that the barrels themselves were apparently put in different, you know, they were in Japan at one point. I think, James, you mentioned earlier on that the barrel had a label that was past its use-by date, and apparently the barrel had been reused, but we can't confirm that because the logs were not kept up to date. And there was a position available, hazardous communication support program manager was not in post. And there were various people getting swapped out over time. So there was changes in the control structure. So there's a few other comments there. Rajiz, hi Simon, thank you for your impressive presentation. I have a meeting and have to leave the meeting. Oh, fantastic. Okay, well, thank you. Hope you would share the recording. I'll see what I can arrange. Thank you. It's great to see you. Carol, my question is how to avoid situations like this. One, if trained staff is ignoring simple rules about protection of aircraft systems from water. This topic is an important part of any training of maintenance staff. That's a fantastic question. As part of this control structure model, if we were involved in the investigation, we'd go and interview these people. We'd have a look at their maintenance procedures. We'd have a look at their policies. We would talk to them and ask them, starting from the physical process, you know, maintenance team member L5, L7, why did it make sense to use the hydraulic service handcart? Okay, do you know who is involved in making sure that hydraulic service handcart is serviceable and appropriate for flights, you know, putting stuff on flights onto aircraft? Do they know who's involved in the hydraulics barrel control and monitoring? Do they know who's involved in the fitting of the pump and refilling the barrel? These people, if I stretch this, they might literally be involved in all of this. You know, it might be that they are the key people, but we don't know that. I'm just postulating now. So yeah, it's great you're asking those questions. There's loads of stuff in there. I mean, in terms of training, what training does is it essentially improves or gives the people involved new abilities to make decisions, new control algorithms, perhaps even new control actions or different control actions, or it specifies how they should provide control actions in what order. You know, such as you might say that if they, you know, in the future to prevent this kind of thing happening again, the question might be, we're going to give you a new control algorithm. You must check the hydraulic service handcart and the quality of the fluid in it before you use it. So you're sort of expanding their responsibilities for the hydraulic service handcart, and they're now responsible for doing that check. But again, if they're using equipment like this portable oil diagnostic system, and maybe there's only one available on the squadron for argument's sake. If someone else is using it, maybe if this aircraft needs to get on the flight line and go flying immediately, maybe they'll decide not to do that. So there's a lot of human factors aspects there as well that we could explore, but we don't have enough information in this investigation report to talk about it. Emmanuel, will the video link to this section be shared with us by email? I'll see what I can arrange, Emmanuel. I need to check whether it's recorded properly. Jose, STPA can be used to analyse this situation, which is complex due to work pressure. Yeah, absolutely. We can certainly do that. Okay, so I'm just looking at the clock. There's so many more things we can talk about. I'm open to you to consider what do you want to talk about. It's open to you. Tell me, what do you think? You're welcome to type in the chat, or you can put your hand up and I'll bring you on the screen and we can talk about it. Dave Cummins, hello mate, good to see you. Do you have any clear recommendations you think should be made or could be made from the stamp perspective? There's three critical recommendations I would make from the work I've done. The first is, the most critical thing is this flight control system design. I am really uncomfortable that it appears, based on limited information in this one investigation report, that the process model inside the flight control system software is reliant only on these weight on wheel sensors, and that feedback is inadequate, because there must be other feedback available on the aircraft via the data via the data flying around the aeroplane, that I'm sure wouldn't be too difficult to make it available to the flight control system. And I probably deserve a slap for saying that, because these systems are very complex, and maybe what I say sounds really basic is maybe 50 million to fix, and maybe 50 million's worth it if you lose another aircraft, to put it that way. So that's the first thing. The second thing related to that is this weight on wheels logic. And is that really a robust, high-integrity feedback path that gives the aircraft a true belief that it is on the ground or in flight? And I would argue that perhaps they might want to consider, if not already, some kind of pilot override. Like if you literally select full afterburner immediately after taking off again, the aircraft should be able to know that that's the state it is in. On civil air transport, you've got the take off and go around, toga. So when you slam those throttles full forward, a switch or two switches, depending on the architecture, will feed back into the throttle control system and into the thrust control system to tell it, and the flight control system, hey, we're at full power here. Don't go doing anything silly like initiate thrust reverse or something like that. And in fact, some aircraft and some accidents have occurred because of coordination issues between thrust and thrust reversers, auto throttle and thrust reversers. I can't think of a specific example, but there has been a few near misses with that. But again, the STPA is perfect for that kind of topic, because it's it's an issue with complex interactions and timing, and STPA is perfect for that. That's what it's really good for. And as I said, Air France 447, I think, is related to similar sort of thing, though not weight on wheels, obviously. More to do with flight data. But yeah, so does the mishap pilot have an ability to override it? If they think, things are misbehaving, can they revert it to a safe control law? I'm trying to think. There is some. I've got to be careful what I say. Let me have a think. There are some aircraft I'm aware of that are used for flight research, and they have normal flight control laws to get from the airfield to the test area over the sea or wherever it is. So if they have a problem, they can ditch it and not worry about it. And they have flight test laws, and they engage those with two keys, somebody in the back, somebody in the front, whatever it is. They go and do whatever they're doing with these new control laws, and then they physically disable them and return back to flight, return home. And of course, if they have any misbehaviors with these new control laws, they can immediately disable them. But that is in flight test. That's not in production operations. That's not in, normal flight. That's with test pilots. So I don't know if that's available or not. But they're the two. For me, if I was working for Lockheed Martin and supporting them, I'd be drilling into this like crazy, getting everyone together. And that video of the F35B I showed you, I'm hoping you can start to see, well, hang on a minute, I've just watched this video, I've modelled this control structure in my brain, and I can now postulate how this accident's occurred. There's something wrong with the process model in that flight control system. It must believe that it's falsely on the ground when it's not, the second thing is this conference hotel. The control structure for the conference hotel and the ability to make a phone call while the plane is in the sky, that just blows my mind. That should be audited and looked at with a control structure. Who are the SMEs, subject matter experts, in that conference hotel? How reliable are the communications connections? You don't want the cleaner inadvertently pulling a plug out and plugging the vacuum in and turning off your access to the conference hotel with the aircraft. The second thing is that the makeup of that team, my view is you must have a set of people commensurate with the functions on the aircraft present in a shift online, ready to go whenever the call comes in. And past experience 20 years ago now, when I was working at Rolls-Royce, I was working in technical support and overhaul, so I was looking after their large fleet jet engines, the big engines for 747s and 787s and Airbus A380s and stuff like that. And they established a 24-hour control centre that was manned with people that knew everything about everything to do with the engine and the aircraft and the interfaces and all the components. And they had immediate access into the factory to talk to frontline workers who knew everything to the micro detail. And they were set up specifically to be able to provide 24/7 cover. And they scheduled people with that in mind. And now in their context, they just started doing power by the hour engine supply. So they provided the engines to the airlines. And if the engine was not working or it was, the aircraft was AOG, Rolls-Royce were getting charged. So obviously it was in their interests to make sure they were giving tip-top support, tech support immediately to all their customers. And ultimately that led to a better relationship, a safer relationship for the customer. But also it meant that the people in the teams, they became technical experts in pretty much everything across the team. So it was great for everybody, but obviously it was even better for safety. So my second recommendation is we need to seriously sort out this conference hotel. This is a safety management system issue here. So again, Lockheed Martin, US Air Force, Department of Defense, something needs doing about that, because that's going to contribute to other accidents, I would suggest. That's the second big issue. The third issue is from a maintenance perspective, and I think you've already highlighted this. What the heck is the control structure for making sure these aircraft, these very expensive, high-performing, aircraft, what is the maintenance for that? What is the control structure for that? And I'd obviously focus firstly on hydraulic servicing, but I'm sure you know where I'm going with this. This accident indicates that the control structure is inadequate in some shape or form. So what does the control structure look like? Who or what is involved in it? What are the interactions between them? What are the unsafe control actions we need to protect ourselves from? And this is just this is just highlighting one example of one major weakness with that control structure, whatever it looks like. So I'd argue, because that control structure also does other maintenance and servicing, there is other risks not related to hydraulics to the aircraft and their safety, but also from an occupational health and safety perspective. Because these are hazardous materials. You don't want to mess around with hydraulic fluid. And when you're operating and working with the aircraft, you've got high pressure, energy in these oleos and other things. You don't want that control structure to hazard the aircraft. So that's my third recommendation. What the heck is going on with maintenance in that location? And is it constrained to this squadron, or is it across this airfield, or even across the Air Force? Is it a systematic issue? Is there something wrong with the training of these people? Is there something wrong with the Air Force policies? Are these policies inadequate? So yeah, there's my three. If you want to send me an invoice in the post for send me a purchase order in the post. That'd be fantastic. So Ruben says, safety information system. How does the information is disseminated to the people who need to make decisions that impact safety? Examples to look into based on what you mentioned are the newsletter. Yeah, fantastic. That's over here. So, well, actually, that's my fourth recommendation. What the heck is going on with these maintenance newsletters? I'm not being funny, but that should not be a newsletter. That should be a formal safety signal of some description that everybody must be made aware of, and there must be some kind of feedback to confirm that they understand it. Now there is a bit of a balance there to be had, and the example I'll give is back 20 years ago now. I used to be a glider pilot, conventional glider, and supporting an RAF volunteer gliding squadron. And one of the things we had to do was read all the notice to airmen, the NOTAMs. And I'm not joking, it was like this thick, an A4 binder this thick full of NOTAMs. And because the airfield we flew from, RAF Syerston, it was in a particular location that had a lot of other RAF stations around it, flying training stations. And of course, you don't want a glider and a fast jet to come into contact. And of course, when you're driving the winch, because these were winch launched gliders, I used to drive the winch. It was fantastic. You don't want someone to go flying through the cable when you're winching someone into the sky. So there's a lot of NOTAMs you have to read. And of course, from an operations perspective, a glider doesn't have an engine, so you need to have your wits about you when you're doing that. So yeah, the safety information system is absolutely critical, and that would be my fourth recommendation. So if I go up here, look, so part 3 of CAST, structure analysis. Ruben highlighted the safety information system, which I've already underlined. So that is a critical element to this as well. And again, just to emphasize, safety information system, while it says SIS and it sounds really formal, a safety information doesn't have to be formal. It can literally be somebody sending an email that contains important information, but it's not formalized. I'll give you an example. This one of the examples I've been looking at for the Healthcare Safety Investigation Services Investigation Branch. The case that I looked at was a child that had been overdosed with a particular drug. And the reason they'd been overdosed is because the doctor who'd calculated the drug dose, they had captured the dose information in an email sent around a particular list of key people. But they didn't include the dose information in the electronic record system, the EPMA system. And so when the nurses were getting the dose of drugs to give to the patient, they noticed that the drug dose was very, very high. And they're like, hang on, this is a bit high, this one. But because it said in the electronic records that the dose had been discussed with XYZ experts, the nurses had come to believe that that dose was correct. But actually the dose was not correct. But there was no way for them to know about it. And because the doses were administered over the weekend and those doctors were not available, they didn't detect the dose until later on. And so electronic patient records, some people argue, well, they're not a medical device, or they don't affect safety. And emails should never be used to communicate safety-related information because they're not reliable. That not everyone's going to get it. And how do you confirm everyone's received it? And what I'm highlighting here is, if you're communicating safety-related information like that, it should really be formalized in some shape or form. It shouldn't just be an email or a newsletter. It should be, have appropriate integrity. And I think I've banged on that a bit much. So what else did Ruben say? Let's just get that back on the screen again. So it doesn't quite fit on the screen, but let me get the last bit. So the newsletter and the safety advisory, yeah, absolutely. B, keeping logs up to date, probably others. Yeah, so these logs, the logs about the hydraulics barrel and the use of the portable oil diagnostics system. So the actual, sensing what's in the hydraulic fluid and whether it is not contaminated or not. Yes, those logs are part of the safety information system. So Kevin Hayes, I was surprised that water in the second aircraft was not detected until a near miss happened. Ooh, Kevin, fantastic. That's something I've not modelled in my control structure. That's a good one. So what you're saying is the feedback from this accident, this control structure, how does that feedback, knowing there's been an issue, an incident, how does that actually find its way to operational flying, from frontline flying? No, it's a fantastic question. So I'm pleased you've asked it, because it's something I need to emphasise in the future. So this case study is purely about what's in that investigation report, and that they haven't, because I'd not appreciated the point that you've made. I just focused on this particular jet, and I didn't actually bother to go and model the control structure for actual flight operations and the feedback loop that is essential between this investigation and this accident and that flight operations. And so the way that I would address that is I'll just quickly put my slides back on the screen so you can see. No, not my slides, live screen. There we go. What I would do is I'll just quickly duplicate this and put it down here like this. What I would do is recognize that these go to all the jets, not just this particular one. So that maintenance aspect there, it's all the jets. So, whoever's interfacing with those jets, if they're using the same hydraulic handcart, they should have dealt with that. But from an operations perspective, I'll just move this over here like this. I'll stretch this controller over here like this, and I'll highlight that there's other jets that they need to take care of. So other jets, flight line, what are they doing about that? Are they providing other control actions to that? They say, look, we've just had this near miss with this, we had this crash with this jet. What does this control action look like? Ground other F35s, check for contamination. Is that a control action that they should have immediately provided? Did they provide it? If they didn't provide it, why did it make sense not to provide it? That's a fantastic question. I don't know how we could answer that. And the same... Oh, exactly, yeah, why didn't they pick it up? And I suppose you could also say it should also come from the manufacturer, and that would go to other... Sorry, I'll put over here other commands, Air Forces. There we go, that control action should go there as well from their perspective. So has that gone out? Did it go out? Don't know. Yeah, it is a bit strange how the aircraft got took off. I'm so pleased you've highlighted that, because that really brings this to life, But yeah, what other things would you like to talk about? Are there any other questions or comments or concerns? So there is HFACs. Some of the language in HFACs does cross-link with the language used in STPA or CAST, but it's not a complete one-to-one relationship. There are things in HFACs which are, everything in HFACs, in my opinion and experience so far, is that everything in HFACs is covered by STPA or CAST in the type of control actions, unsafe control actions definitions, so timing, duration, sequence, and all of that stuff. And then in terms of, acts, I don't know if you can see on the screen, is it big enough for you? I'll just zoom in. That's as far as I can zoom in. Is it big enough for you, that, or can you see that? Yeah, so 4 main categories in HVAC. So acts, you could say that is a direct read across to control actions, or unsafe control actions, contributory control actions. Preconditions, that could cover things like beliefs or decision making, or maybe the context within which a controller is doing some activities. Supervision, so in the case of maintenance, there was a lack of supervision because there was no clear controllers in the higher level parts of the control structure. And then organisational influences kind of covers those aspects as well. It's kind of overlapped. So there is a synergy there, but it's not a direct read across. And as you quite rightly point out, the ones that are highlighted in the report, they are quite high level. But I'm hoping you can see from what we've done tonight that if you had the detail, if you were in part of the investigation and could ask the questions, using that control structure model, you could drill so much further into why did it make sense for this controller to behave the way that they did. What were your beliefs? What were the control actions you provided? What were the interactions from above, from elsewhere in the organisation? What contexts? Why was there such a high staff turnover in the maintenance team? And I said this on the podcast with TJ Candy last week. If you have high staff turnover in your safety control structure, that indicates that something's not right and will likely have a consequence for safety. So people should pay attention, leadership should pay attention to that. But of course, if all layers of leadership are suffering the same issues, then, it's kind of inevitable that something, a near miss or something more serious is going to happen. So fantastic. Well, thank you for coming on. Let's go down the list and see who else there is. Thanks a lot. Right. That's not that button. It's this button. There we go. Fantastic. Right. So I've got some more questions there. Dave Cummins says, perfect. The LM guys will owe you. Yes, I'm hoping so. If anyone's from Lockheed Martin or the Air Force, please get in touch. James Savage, speculating I know, but there is also the suggestion that having the appropriate skills and knowledge on the conference call might also have changed the outcome. Yes, absolutely. That is certainly an aspect. Fantastic. Okay, so that was a bit of a whistle-stop tour. There are still 10 people on there. Thank you for staying with me. What other questions, comments, concerns, compliments, commiserations do you have? Or should we move on to the final session and call it an evening? Well, for me, STAMP, STPA or CAST is fundamentally part of the safety management system. And I think I mentioned this on one of my videos recently. The FAA, Federal Aviation Administration, they define a safety management system as having 4 parts. If I remember correctly, it's safety policy, safety risk management and assessment. The third one is safety promotion, so training and things like that. And the final part, I can't remember, someone could probably mention in the comments. But my view is there's a 5th element, which is the safety control structure. And if you model that safety control structure for your, if you're the maintenance manager, you could create a control structure model for all of the maintenance tasks or hazards that you're involved in. And of course, from an operational aircraft perspective, there will be links between those control structures and how they fit together. And like I said, I'm really, really pleased with Kevin, how he sort of emphasized the point about how does all of this stuff actually link back to safe operations. So if you have a near miss or an incident or an accident, what are the immediate actions that your others need to take to avoid a similar accident? And if they're not happening, such as they didn't in this case, why the hell not? That's really important. So thank you for that. That's amazing. Are there any other things you'd like to discuss, or shall I jump back to the last few slides and we can call it an evening, call it a day? Okay, so let's put the slides on then. So, there we go. Dave's just said something. Dave Cummins. Hi, Dave. All good comments. The traditional process likes to look at things in isolation as individual failure conditions with bounded assumptions that are often not tested out as well as they could be. STAMP allows us to look at things in context. Yes, it does. Yeah, I mean, I'm hoping you can see from thinking about things through the lens of these little, jigsaw pieces, the control loops and the control structures, you can see issues that occur right over here. For my hands on the screen, could be an issue here that's apparently remote, but actually it affects something directly over here. And an example of that I'll share from years ago working in air traffic control, where they like to use bow tie analysis. In fact, actually, hands up. Let me just get that on the screen. No, not that one. Effects. Let's just have a show of hands. How familiar are you? Do you use bow tie analysis in the stuff that you use? Let's just have a quick chat about that. Dave says he tries not to. Anymore. So we've got a few there. Okay, so 10 years ago, I think. Yeah, about 10 years ago. God, it's a long time. I'm getting old, proper old. Yeah, so 10 years ago, I was doing some work in air traffic control, and we were looking at changing the lateral separation between aircraft going over the ocean, going over the North Atlantic. So at the time, they had the North Atlantic track structure, where the aircraft were basically a set amount of miles apart, and that was that was to give them safe separation if they need to turn round and come back. Because of course, passenger jets are not like fighter jets; they can't just stand it on its tail and come back. They've got all these people drinking their martinis and gin and tonics, and you don't want to spill them when they're going over the ocean. So they have to do a gentle turn, nominal 1G to get back. So they need a big area to turn around. And so the point of the project was essentially to reduce that lateral separation using a new technology called space-based ADS-B, which is essentially providing flight data about location, speed, altitude via satellite back to the air traffic control centres, so they can use it as a type of pseudo radar, because you don't have radar over the ocean because it's just too big and there's not enough radar stations. But using space-based ADS-B, you can take data from the aircraft and the aircraft's navigation system, beam it via satellite to the air traffic control centre, and then they can see it on a display. And so given that new feedback to the air traffic controller, logically, the thought goes you can reduce lateral separation and then send them text messages, so text-based air traffic control. I can't remember the acronym for that, but essentially they can issue instructions instead of via the radio. And typically over the ocean using HF radio, it's not very reliable. So being able to send text messages via satellite means they can control the aircraft over the ocean, so logically you can reduce separation. And as part of the analysis with all of these air traffic control experts and systems experts, they were all talking about what the hazards were and what the causes and consequences were through the lens of a bow tie. And me being me, I did a back of the fag packet control structure model, and I highlighted two scenarios. One scenario was, well, what happens when an aircraft entering the ocean area loses their capabilities, loses navigation or communications, so they can't give you that information? What do you do then? And they were like, oh, well, the probability of that happening is 1 to the minus whatever it is, so it doesn't matter. And I said, well, that's not true. You've got to understand that the equipment you're talking about on board an aircraft is not flight safety related. So if it doesn't work, it's not going to affect the aircraft. And if it's not going to affect the aircraft, the integrity of that piece of equipment, software, is not going to be the same as the flying control systems, for example. So your reliability, your probability number that you've just made up out the top of your head is not appropriate. And if you want that number, because you've decided that's the number you need, 1 to the minus 7 or whatever it is, then you need to make sure the equipment manufacturer and the certification agency places that requirement on them. And of course, that then implies certain architectural things, such as, I don't know, dual power supplies to the avionics box that's going to provide your data. And they were like, well, we don't need to worry about that because that's not air traffic control. And I said, well, hang on, from a control structure perspective, you are now placing dependencies, important safety dependencies, on that avionics. And if you're not going to tell them about those, new requirements, then they're not going to know. And so your system is going to be either highly unreliable and not safety related, or you're going to have safety issues, especially if you have a situation like September the 11th, when the whole ocean turned round and came back, and you had a really big airspace issue. So, and they wouldn't have it, because in their mind they were thinking about bow ties. They were thinking about their bit of the control structure, and everyone else can do their own work and solve those problems themselves, and that's just not appropriate. And then the second issue was to do with, well, what about space weather? What if you have a solar flare that affects your ability to control, receive feedback and issue instructions? What do you do then? Let's say we have a solar flare that's really bad and lasts for, 2 days. Do you still use those same procedures? How does the air traffic controller know that there's space weather on its way? How do they know what effect it's going to have on their systems and whether it's safe to do what they're going to do? And they were just like, oh, well, that's space weather. We don't have to worry about that. We're air traffic controllers. We don't need to worry about space weather. And I was just like, look at the control structure. Are you going to screw these bits of the control structure up unless you know about space weather? And they just, anyway, it was just a bow tie. I want a bow tie and I want it on an A4 page. I don't want any of this control structure nonsense. Anyway, I'll not talk about that. I ought to maybe do a challenge on LinkedIn. Show me a bow tie. I guarantee I'll find holes in it. And if I don't find holes in it, I'll do it for free. That's what I should do. So yeah, Jose, thanks. Dave Cummins, this is part of why exposure mitigation is so weak. Do nothing because think conditions I can't control are unlikely. Yes, absolutely. This is it. They try to dismiss them by saying things are black swan. Oh, space weather, it's a black swan. We don't need to worry about that. Oh, September 11th. We'll never close all of North American airspace in one go. That'll never happen. You know, I'm just moaning now. That is an important point. Human factors of managers cannot deal with more than a couple of variables. Absolutely, yeah. Dave Cummins, there is a lot of criticism in the IMEC's alert guidance of Bowtie. Bowtie allows people to mislead themselves into a false sense of security. I used to call it Bowtie bingo. Bowtie bingo, absolutely. Right, so let's jump back to the slides then and keep going. So slides, that one. No, not that one. There we go. Here we go. Right, so just to sort of sum all that up. So what I've done today is a very, very superficial go at a stamp foundation training for you today. I've told you a bit about the what and the why and a bit about the how. We've gone into some more detail in the context of this accident. Now, if I was giving you a full training, I could talk about this for literally hours and days because I'm very passionate about it, and I want people to succeed. I don't want people to, suffer like I did in the early days, going around in circles, fighting against the status quo, getting angry and stressed and annoyed, and thinking that, yes, this is a better way. Why won't people listen to me? This is certainly going to solve a lot of problems. Let's move forward. So I want to provide that support to you. I want to create a community of like-minded people to get together, support each other, and move forward in their journey of learning STAMP, STPA, and CAST, and then applying it. Because the principles are pretty basic. The control loop jigsaw piece that I highlighted today, that is the core to everything. Once you embed that in your brain, you're going to be seeing unsafe control actions everywhere. When you start thinking about the jigsaw puzzle, the control structures, you're going to see issues all over the place, and you're going to want support in not going crazy, but also moving things forwards and transforming things. And so that's what I'm doing in the future. I'm starting a foundation program to give people that start in the world, with the view to then, graduate them into something a bit more detailed, a bit more advanced, so that I can support that growth. And that's what I want to do. So if that is of interest to you, if you are, if you want to move forwards, if your organisation wants to move forward, and you need that outside help, you need somebody with system safety experience across many domains, who's got the arrows in the back, the injuries, the experience, the tears, the blood, sweat, toil and tears, and not just an academic perspective, but a real life experience perspective, then I'm here to help. So please send me an email. I'll give you my details in a moment. Send me an email. Let's sort of set up a call. We'll see where you are, see where you want to get to, and I will help you to put a pathway together to follow, and then I'll support you in your journey. It is a lonely journey, and you need as much support and people around you as possible, because it is not easy. The principles are straightforward, but the practice is very challenging, and you can do it yourself, but I'd recommend you get support because it can be very challenging mentally. Right, so final thoughts and reflections then. So STAMP provides a framework that creates insight into the system and its design, operation, and it is unique and powerful. I'm hoping you can see that, you can agree with that. An accident, incident, or near miss reveals the control structure is inadequate in some shape or form. And if we were talking about root cause analysis, and I'm going to be a bit facetious here, but for me, the only root cause is literally the control structure is inadequate in some shape or form. It could be inadequate in one place, it could be inadequate in many places, and I'm sure you've seen from this example, this case study today, that there was loads of inadequacies all over the place, and we basically wasted $200 million and nearly lost another $200 million 8 days later. So, this approach can save megabucks. Stamp-based analysis focus is on the control structure and controller behaviour and interactions. It is not just failures. It is about failures and dangerous successes. And I've just stolen my own thunder. It goes beyond failures, faults, and it includes dangerous successes. And so it's especially good for dealing with software. And if you talk to people who talk about software failures and software failure rates and trying to put numbers on things, this stuff will annoy them because it removes that burden. You don't have to worry about numbers now. Unless, of course, your regulator wants some rubbish, made up numbers, then, crack on. But if you want to actually deal with safety issues, then this is the way to do it. So this is a massive, you've seen from this investigation report, we could have saved $200 million. We could have saved another $200 million 8 days later had we had, Kev on the team, and Kev said, hang on, what about the other aircraft in service? So this is very valuable, what we're talking about here, and it's very important. It will save lives. And especially if you do it in the system development, early in the system development life cycle. If we'd have parachuted in with those Lockheed Martin software control system engineers and said, hey, it'd probably be a good idea to have more feedback into our process model than just the weight on wheels switches. And they say, oh, well, the weight on wheels switches have a failure rate of 1 to the -7, so we don't need to worry. And we're like, no, this is not a failure. This is a dangerous success. We get a genuine weight on wheels when we're not on the ground. So what are we going to do about that, everyone? And of course, it covers both safety, security, and accident investigation. So if you want to go into the security stuff as well, there's 2 extensions to it. I won't go into the detail now, but the first is, don't assume that everybody is coming to work to do a good job. Think about adversaries. How could an adversary undermine my control structure and cause an accident or cause a security issue? And I'll just emphasize this, that is why I do not recommend publishing your control structure models. If you're ever going to, your control structure models, once you start adding detail, they should be classified in some shape or form, because you're basically doing the groundwork for an adversary. If an adversary built a control structure against your system, they could find holes in your system to exploit. So why would you share your control structure detail with them so they can use that as a starting point? And also for near misses, incidents, and making recommendations, you can improve. If an incident occurs, your control structure is inadequate, and you've got an opportunity now to talk to people and investigate and interview them. Because if the people are not dead, I'm hoping they'd like to talk to you and tell you what's happened. So that is an opportunity to make things better. Now, there is a potential threat. And in my training, I always bang on about the SWOT analysis: strengths, weaknesses, opportunities, and threats. One of the strengths of STAMP, STPA and CAST, is it finds stuff, and it's very good at that. And it allows you to look so much higher up the control structure through leadership, even to the government and regulations and beyond. But with that, it's a threat, because now you're able to ask questions and hold people, ask questions of people that probably don't normally get asked questions like this, certainly not specific questions, and they will be uncomfortable getting these kind of pointed questions. The conference hotel designer, for example, I would probably, if I was a betting man, I'd say that the conference hotel is not designed in the way we design a technical control system. It's probably based on past experience and good luck. We've done it this way before, not had any problems, so it's fine. So they're probably going to be a bit uncomfortable getting asked these detailed questions, and it's going to be difficult, uncomfortable, and probably unwelcome to deal with. And just be mindful when you're in an organisation that's using this stuff, when you are trying to bring STPA or CAST into an organisation, you have to be mindful about whether that organisation is potentially hostile to you finding new things. Because you as an individual, you've got a job, you've got bills to pay, kids to feed, all of that good stuff. If you start raising issues in an organisation, the organisation might, have an allergic reaction to you and manage you out of the business, so you might have stress and everything else. And I don't want you to fall victim to that. So just be mindful. Maybe your escapades might be better served somewhere else. But that's a safety cultural argument we talk about another time. So questions and answers then. How can you see this helping you in what you do? What benefits can you see? What challenges can you see? What support do you require, whether that's training, coaching, facilitation, consulting, or independent review? What other questions and comments do you have? And how can I possibly help? So it's open to you. If you'd like to raise your hand, I'll bring you on the screen and we can have a chat, or you can stick it in the chat and I'll bring it up on screen. Jose says, I'm still fighting. Dave, you understand. Software and humans, yeah, absolutely. Agile, yeah, I have been fighting Agile. Both the pressure from project management to be Agile, whatever that means, and also the Agile set of tools such as Jira, where everything becomes a task and everyone drowns under emails. That's not good for stress or safety. Or is everyone fallen asleep now? You know, have I done so well? My voice has put you to sleep. Fantastic. All right, well, let's just move forwards. So yeah, contact information. If you want help, you are welcome to visit my website. I'll just bring it up on the screen now. Large screen share. There we go. This is my fantastic website. I need to make it look a bit easier because it's a bit busy. But if you press this big green button in the middle, it says I need help now. Type your details in there, name, email, phone number, message. Tell me how I can possibly help. We'll set up a call. We'll find out where you are, where you want to get to, and I will help you put together a plan to deal with that. And if you need help executing that plan, I am available to do that. I am putting my calendar together for 2026. So trying to fit things around, well, I say trying to. I'm going to fit things around my Space Mars work and my Health Safety Investigation Board work. But 2026 is looking open, so if you want some help, we can fit that in. And even now, if you want some help literally right now or this week, next week, I can arrange something, we can work together. So that's my website. And that's it. I just want to say thank you. It's been absolutely fantastic. I hope this has been a benefit to you. I hope it's given you some food for thought, some ideas. And again, please get in touch and we can work together and do some fantastic things. So Dave says, well done, Simon. Thanks for sharing all your thoughts and experience on this. Very kind of you, enjoyable to be part of. And you're most welcome, Dave. It's great to see you. Thank you. We should get you to do one of these sessions. Carol says, many thanks for a deep insight. It helped me very much. Safe flights. Thanks, Carol. Appreciate it. Donald Patton, appreciate the effort you place into doing this. Incredibly insightful. Thanks, Donald. Really appreciate the feedback. Kevin says, thanks for all the hard work in putting this together, Simon. It's been a very interesting few hours. Thanks, Kevin. And thank you for your comment. I'm going to feast out on that insight for a good few months. And Jose says, many thanks, Simon. Thanks, Jose. It's great to see you. Everything. It's been a genuine pleasure. It always is. And I look forward to seeing you on the next one. If you've got any ideas of what else you'd like me to look at and talk to, then I'll be sure to look at it and maybe run another session. So thank you very much. Take care. Have a good night. Bye-bye.